Yeah, so good afternoon, everybody. Pointer is not working.
No, you have to point it to the computer.
Okay. So I think today you have heard a lot about what I will call topic-based meta-analysis. So the idea is I think this is the most common concept that we have when we think of meta-analysis. So the idea is just that we are interested in a particular behavioral function or a particular behavioral concept, and we want to know which brain region are related in activation data to this concept. For example, working memory, what are the brain region consistently related to working memory? But today I'm going to talk about something slightly different, which I will call location-based meta-analysis. So the concept is just completely different because the idea is that we want to derive brain region consistently found to be activated together with a specific other brain region. So now the focus is not on a behavioral concept anymore, but on a brain region. So we start from a brain region, not from a behavioral concept, and we go across a wide range of behavioral functions. So we don't look into a specific behavioral function, but we look for a given brain region across many different behavioral concept, behavioral function. So basically, let's say, for example, we are interested in left M1. So the idea is that we look at what are the other brain regions that are usually working with M1, that are usually co-activated with M1 across a wide range of experiment. And what it gives us is basically the functional network of M1. So it is a type of functional connectivity because these are the regions that are functionally connected to M1. So just to locate this type of connectivity, what you might already know about connectivity infer from neuroimaging scanners. So the most straightforward connectivity is physical connectivity, so that we measure with diffusion, anatomical connectivity, for example, when you use probabilistic diffusion tractography. But you might also look at functional connectivity with MRI data. So here it's referred to statistical dependencies that we observe between brain region, in the signal of brain region. And one way, the most popular way to doing it is to using resting state data. So basically, you take a group of subjects, you put them in the scanner, and you record their brain signal when they are lying at rest in the scanner. Then you perform a statistical analysis or correlation to see what are the brain regions in which their signal are similarly fluctuating across time. So, and this gives a measure of functional connectivity. So this is the most common way to infer functional connectivity, but we could also look at functional connectivity during active tasks. So when the subjects are performing an experiment in the scanner, a behavioral paradigm. We could do that in a specific behavioral task, for example, during a working memory task, but then the functional connectivity that we would get would be specific to the specific behavioral task. So that wouldn't be a robust profile of functional connectivity. And one way to have a robust profile of functional connectivity during active tasks is to use a meta-analytic approach. And this is what we call meta-analytic connectivity modeling. So we look at connectivity for a given brain region across a range of different behavioral tasks, and we compute the consistency across those tasks. So how does it work concretely? First, we have to get the coactivation found across different experiments, and we use that as we use the pattern that we get as an estimation of functional connectivity. Yeah, this is what I just said. Okay, so the material that we need for doing that is a range of activation experiment. As you have already heard today, I think is that there are already hundreds of thousands of activation experiments that have been performed. And the good thing is that they have been collected. I mean, the result of the experiment have been collected into databases. So now we can access them so there are two main databases. One is BrainMap database, and the other is NeuroSynth. And so they are collecting those results of all those different experiments, usually PET or fMRI experiment with many different behavioral paradigms. So we can compute meta-analytic connectivity modeling from there. I will illustrate this with the BrainMap database. So what has been stored in the BrainMap database is the coordinate of the activation peaks in X, Y, Z space dimension. And we have more than 120,000 locations there. So for a given, concretely, so it has been manually coded. So for a given study, so for example, if you take this study of Brever, it was a working memory study. So for each peak of activation that was reported in the paper, we have the exact location in X, Y, Z, and we have the peaks for each individual contrast of the study. So it was an n-back task, so we have the peak for the 0-back condition, the 1-back condition, the 2-back condition, and so on. And what you can see here is that all the peaks that were reported in this study and that are now in the BrainMap database. So how we're gonna do a MACM analysis from all the studies that we have in the BrainMap database is the first step is to identify all experiment activating the region we are interested in, that we call the seed region. Then we can set some general or specific inclusion-exclusion criteria. For example, we might be interested more specifically in studies that have been performed in healthy adults. Then we have to extract all the coordinates reported in the identified experiment and to perform a meta-analysis across all these different experiments. So these are the main steps. So we can go through it with a concrete example. So for example, I talk about left hem1 at the beginning. So if we want to know which brain region are functionally connected to this region, first we have to identify all experiments activating this region that are encoded in BrainMap database. So for example, let's say here we have all those experiments that have reported activation there in M1. So we have 155 experiments. Then we have to extract the peak that have been reported in those experiments. So if you take, for example, this particular experiment, this was an action-execution experiment, and there were 15 coordinates that were reported there. So we extract those coordinates, and we do that. So here you see like there were 15 peaks, and we do that for the 155 experiments that have reported activation in M1. This is how it looks like when it is projected back in the brain. And so this gives us more than 2,000 peaks or activation foci. And this is the material that we're going to use for our meta-analytic connectivity modeling. So first we have to perform a meta-analysis across all these experiments. So we have to model uncertainty because, as you know, when a peak is reported, there are some spatial uncertainty around each peak, and we use Gaussian 3D distribution for accounting for the spatial uncertainty, and then we perform a statistical test to get the significant region that are robustly co-activated with M1. And how we do that is by, we test the actual ALE score we test them against the null distribution of random association between experiments. Okay, and what it gives us is the network which is co-activated with M1, so the functional network of M1. And if we compare that with a measure of functional connectivity from resting state, you can see that this is quite consistent. So we have a similar pattern for active task and for resting state, despite the pattern of MACM is more spatially restricted, more spatially confined. I mean, this is normal because this is also behaviorally constrained. But still, there are some regions that can be observed with meta-analytic connectivity modeling that we didn't get with resting states. So probably those regions are activated with M1 when we perform active tasks, but they are not their spontaneous fluctuation at rest are not especially coupled with M1. So this is really interesting for better understanding brain function. And this also arcs for the validity of what we get with meta-analytic connectivity modeling. So to summarize, what I have said as far is that we can use coactivation across different experiments for deriving a type of functional connectivity of a brain region. So this is called meta-analytic connectivity modeling. But then we can also use this information, the functional connectivity, for parcellating the brain. So you may know that, I hope you know, the brain is topographically organized, and different brain regions have different characteristics, such as cytoarchitecture. So the first parcellation studies use cytoarchitecture to define different brain areas. And for several years now, we are well aware that connectivity information can be used for defining different brain regions. So for example, if you look at the anterior and posterior part of the hippocampus, they are differently connected with different brain regions. So we can use this information for parcellating the brain. And as I say, meta-analytic connectivity modeling gives us a robust measure of functional connectivity. So we can use this information in turn for parcellating the brain. And for example, this is what has been done here. So in the dorsal lateral prefrontal cortex and in BA44. So they have been subdivided into functional region or functional module based on meta-analytic connectivity modeling. So how we do that concretely? You get connectivity. This is the same procedure, whatever type of connectivity measure you use, but so it's applied with MACM as well. So if you are interested, for example, in the hippocampus, you take the voxel in the hippocampus, and if you take two different voxels and you look at their connectivity profiles or the profile of coactivation, for example, with other brain regions, you see that those two voxels have different coactivation profile. It means that if we look at the coactivation profile of all voxels in the hippocampus, we can then label them or cluster them according to their connectivity profile. And for example, we can distinguish by doing so the anterior and posterior hippocampus. How do we do that concretely? First, we have to do a MACM for each individual voxel within our region of interest, so our seed voxel. Then we have to compute the coactivation of each of these voxels with all other voxels in the brain. And then we have to look at how similar, dissimilar our seed voxels are between each other, and to apply a clustering or a factorization procedure. So with a concrete example, for here in the dorsal premotor cortex, if we want to subdivide or better understand the functional organization of this region, what we do first is that we have to perform a MACM analysis for each voxel there. So for example, if we take this voxel, we compute its MACM profile, so all peaks of activation. Another voxel, we look at all the peaks that were associated with this voxel, and we do that for all voxels within this region of interest. Then we model the uncertainty, but we don't apply a statistical threshold because we want to keep the full profile. And then, so what we have is a connectivity matrix, so summarizing the connectivity between each of our seed voxel within this region and all other gray matter voxels. And this is what we use as an input for the clustering factorization. So we basically, what the clustering will do is that it will look at the similarity, so this is a similarity matrix, between each pair of seed voxels. so the voxels within our region of interest, and clustering them according to their similarity or dissimilarity. So the basic idea is that voxels that have a similar coactivation profile will be put together in the same cluster, and voxels that have a different coactivation profile will be put in another cluster. This is basically what the clustering algorithm does. Oops. And so you can see here the clustering of the similarity matrix. And you can see that what it gives is here 5 different subregions within the dorsal premotor cortex. Okay, so we can also then look back at what are the differences that have driven this functional organization along the rostrocaudal and the ventrodorsal axis by actually doing a MACM analysis, but not on the voxels, directly on the seed voxels, but now on the different subregions that we have derived. So for example, we can compute the MACM profile of this caudal cluster, the green one, and we do so for all the different subregions that we have defined with our parcellation, and then we statistically compare the coactivation profile of our different subregion. And this is what we get. We can see that indeed the rostral subregion is more related to a prefrontal network, a higher cognitive function network actually. The central region is related to the IPS, the ventral one, so the yellow one is related to the posterior superior temporal gyrus. So this is where our differences in the parcellation come from. We have done that for a couple of regions. They are not all illustrated here. There are other brain regions that have been parcellated into functional module based on this approach. But they are all the parcellation are available in our database, which is ANIMA. So you can go there and you will, for example, the dorsolateral prefrontal cortex is there, and you can either look at the parcellation, or you could directly download the cluster, so you can then use them for a specific analysis. Let's say you are interested in studying different change in different brain region in schizophrenia. You can download those clusters and use them directly. And also the PDF of the paper is available there, and everything is coded, documented. Okay, so in summary, as far you have seen that topic-based meta-analysis can be used to identify network associated to a specific behavioral function, but location-based meta-analysis can also be used for examining the profile of coactivation of a specific brain region. Then we can also use this, so this gives us an estimate of functional connectivity, which can be used in turn for brain parcellation. Okay, so thank you for your attention, and feel free to ask questions, please.
You're doing well, keeping to schedule. Any questions for Sarah? I think for the sake of time, we'll just move ahead. And oh, I'm sorry, there's a question. Sam.
Yeah, I so when you took the peaks in M1 and you put them all together, and then you thresholded them.
So I took all the peaks of the different studies that have reported activation in M1. So they were not only in M1; they were at different part of the brain.
So my question is then, how did you? I think you said it, but I couldn't understand how you did it on the null hypothesis.
On the what? Sorry.
How you resampled on the null. I mean, you did it in order to simulate under the null. You did something.
You mean the null distribution?
Right.
That's what you mean?
Yeah.
How do we do that? I think Simon has some new development there, right? No? Sorry?
Well, mainly it's the classical AL. So as you just described, against null of random spatial distribution. What we are playing with at the moment, there's one paper out by Robert Langner, I think last year, is actually using the BrainMap distribution as a null. And that gives actually quite some interesting discrepancies. And we're not quite sure yet what's the better way. So if you do a random spatial association as a null, you almost inevitably get regions like dorsal, anterior, insular, posterior, medial, frontal, cortex, and so on, just because they are basically activated and hence co-activated anywhere. Yeah, so they're just very, very frequently activated. Now the thing is, this may or may not what you're interested in, because you can also do the reverse and say, well, I take into account the null distribution in BrainMap and see where is the co-activation probability higher than the per se activation probability given the structure of the database. We are currently semi-happy with either approach, because neither seems to be exactly what you want to see. If you go for the non-corrected approach, this gives you definitely more of the overall co-activation pattern, but it trends to be somewhat dominated by this super frequently activated region. If you actually correct for the base probability, the base rate of activation probability in BrainMap, you're losing these, and you're almost losing them completely. So even regions that you know should be coactive and are functionally densely connected to anterior, insular, and SMA, for example, you don't get them as co-activations anymore, because basically they're always co-activated. So we need some way of combining or calibrating that. It may come down really to what you consider to be co-activations. And that mainly comes down to what are things like dorsal, anterior, insular, and SMA activations. Are the epiphenomena that we're not interested in, or are there actually things that we are interested in? And I wouldn't be able to tell.
Well, we should stop there. So let's thank Sarah again.
Okay.